Welcome to the Copper Spice YouTube channel, and thanks for joining us. In this video, we are going to provide a general description of what it means to link a program and why you should care about the process. Linkage. Linking is often viewed as a simplistic mechanism to bundle together a bunch of files and ship an executable. In reality, it is not that simple. There are several steps which take place when linking a project, and they are slightly different for each platform. The end result of linking is, of course, to generate an executable or a library. Understanding the fundamental principles of linking can influence the structure of your program and help to explain why a monolithic design is not optimal. Link errors are not as common as compiler errors, and usually the message associated with a link error is very limited. Learning some of the basic types of link errors will save debugging time. A deeper knowledge of the linking process helps explain the trade-offs associated with an anonymous namespace, explains why the keyword inline is so important, and why your application builds and works on one platform and yet it crashes on another platform.
One of the most important things we do as programmers is structure our programs into components and reusable libraries. When your program consists of more than one source file, there are many choices. You must decide where classes should be implemented. Do you want to use global variables? Should a CPP file be included in another CPP file? Or should every common group of classes be in a separate namespace? On platforms like Windows, there are additional concerns. If you have multiple libraries which may depend on each other, how do you organize your code to avoid circular dependencies? The linker is responsible for combining all the object files in your program together with any required external libraries. The output of the linker is an executable file or a library file which can then be linked with another application. Before we can examine the linking phase, we need to briefly discuss where the compiler appears and what role it plays. As programmers, we think of the source code we write as being divided into two areas. Normally, each source or CPP file implements a related set of functionality, while the declarations of these functions or classes are located in a corresponding header file. Before the compiler is run, the preprocessor bundles each source file and all the headers it includes into what is called a translation unit. By the time the compiler parses your code, all of the macros and conditional directives will have been resolved. These directives include any #if, #include, or #define statements. The compiler parses the translation unit and then generates an object file. This means that for each translation unit in your program, exactly one object file is generated. Most compilers will toss the translation unit file after it has been processed. Unless you are doing something odd, there will be one translation unit file for each CPP file in your project. This will result in one object file in your build directory for each CPP file in your source. A case where you might have two source files but only one translation unit and ultimately one object file is if you have source file A including source file B. In a standard design, related functionality is grouped together in a single source file. For example, a very common pattern is to place the code for all the methods of a given class in a single source file, which is then named the same as the class. Given the example shown, when booking a reservation, the program may need to create a new customer. The reservation and customer classes are physically located in different files and ultimately in different translation units. When a method in class reservation calls something located in class customer, the compiler cannot resolve this, since the compiler only works with one translation unit at a time. What the compiler does is to make a notation in the resulting reservation object file. The linker is responsible for resolving this notation and inserting the correct calls so everything works at runtime. The terminology to explain this process involves symbols. Each entity, like the customer constructor, methods in the reservation class, or anything which needs to be in the object file, is given a unique name. This name is often mangled and is referred to as the symbol name, or just the symbol.
Each object file in your program contains a symbol table, which is generated by the compiler. The symbol table is simply a map, where the key is the name of a symbol. The value may be a location in the current object file, if the symbol is implemented in the current translation unit. If the implementation of the symbol is located elsewhere, the value of the symbol will be a placeholder indicating its location is unknown. Some languages like C have a very simple way of generating symbol names. The symbol name for a C++ entity is usually mangled by encoding metadata in the symbol name. This is done primarily so overloads of the same function will have different symbol names. Each symbol represents an entity in your program, which requires storage in the executable. These include global variables, functions, methods, template function instantiations, and so on. Note that runtime entities, like local variables, do not need to be stored in the object file and usually will not cause a symbol to be generated. When the linker runs, it examines all your object files and uses a few simple rules to merge the individual symbol tables into one larger symbol table. This occurs regardless of whether you are generating a library or an executable. The behavior of the linker is slightly different on different platforms. For example, when you are linking a library on Windows, all the symbols must be successfully resolved to a location. On Unix systems, a library may contain unresolved symbols, meaning the library is allowed to have symbols which are still placeholders with an unknown location. The assumption on Unix is that these unresolved symbols will be provided by another library or the executable. On every platform, all symbols must be resolved when generating an executable. Here is another example which deals with code in different translation units. Translation Unit A calls the function bakeCookies. The implementation for this function is located in Translation Unit B. Object file A is generated from Translation Unit A and will contain a symbol roughly named bakeCookies. The value of this symbol will be a placeholder since there is no implementation in file A. Object file B will contain a symbol roughly named bakeCookies with a specific location since this object file contains the implementation. When the linker combines these two object files, the symbols will be matched and the call in object file A will be rewritten to call the correct location in object file B. When the program is eventually loaded into memory and executed, the function call is made to the correct piece of code, just as if all the code had been located in one large file. Symbols are divided into two main types. Most symbols in a C++ program are designated as strong symbols, which is the default type. In order for a symbol to be considered as weak, there must be an identification or annotation added in your code. The compiler can also mark a symbol as weak if it meets certain criteria. As we mentioned, one of the steps of linking includes resolving the symbols located in every object file. If there are duplicate symbol names, the linker needs to resolve the conflict. However, if the duplication is between two strong symbols, the solution is to generate an error and let the developer decide what needs to be corrected. The C++ standard has a constraint known as the one definition rule. This rule says there must be exactly one definition for any given symbol. If there are multiple weak symbols with the same name, the implementation needs to be identical. If they are not, the linker will keep one and discard all others. The point of the one definition rule is to make it clear that every implementation of a symbol needs to be the same. As a quick example, say you have an inline function in a header file which refers to the value of a pound to fine. The inline function will be placed in every object file where the header is included. If the pound to fine value varies, then each implementation of the function could be different, and this is undefined behavior.
Linkage is a specific term defined in the C++ standard. Since the standard does not discuss the process of linking, the definition of linkage is phrased in terms of how it affects code in translation units. Linkage has to do with whether a particular symbol name refers to the same entity in the whole program, or if each translation unit will have its own definition. It is important to understand the difference between linkage and scope. Linkage defines visibility between translation units. The scope of a variable is defined as where in a particular translation unit it is visible. For example, the scope of a local variable starts at the point where it is declared and continues until the end of the enclosing block. For a static variable, it comes into scope at its declaration, and it remains in scope until the end of the current translation unit. Every symbol has either internal or external linkage. The default linkage is external for most symbols and internal for any const variable. There are a few ways to override the linkage for a given symbol. The linkage of a global function can be restricted to the current translation unit where the declaration resides by adding the keyword static. This will change the global function from external linkage to internal linkage. The function will then only be visible within the current translation unit and cannot be accessed from outside. A global variable declared without the keyword static has external linkage. This means it can be read from or written to by any translation unit in your program. There are also names which have no linkage. This usually applies to things like local variables. Since a local variable can never be used outside of the function where it is defined, there is no possibility for it to be used by other translation units or even other functions in the current translation unit. Because the linker has no need to be aware of local variables, typically symbols are not generated for them, and this is referred to as having no linkage. A static library contains object code which is then linked with an application. The code from the static library becomes part of that executable. The linker simply copies any required code from the library and puts it directly into the executable file. So a static library is only needed when linking an application. Any changes to the code in a static library will require relinking the application. In contrast, shared libraries are intended to be used by multiple executables. A dynamic linker is used during program startup to load the appropriate code from the right shared library. This is why a shared library is often referred to as a dynamic library. As long as the binary interface does not change in the shared library, you can update the shared library without having to relink the program executable. The ability to use a new shared library with an existing executable is referred to as Application Binary Interface Compatibility, or ABI compatibility. Maintaining ABI is not trivial and not always possible. If you have a method which is implemented in the header file, any changes to the signature or the code in that method will usually break ABI. Maintaining ABI between version releases of a library is something you should consider when updating the libraries your application uses. You should use shared libraries instead of static libraries whenever possible or feasible. The extension for a shared library will vary based on your platform. The mechanism for how shared libraries are loaded is slightly different, and most of the time the details are not very interesting. The one area where platforms differ greatly is how shared libraries are found on disk. For example, on Windows, the directory which contains the executable is searched first for any required DLL file. On Unix, the executable directory is not even in the search path by default. When an application with shared libraries is started, there is an initial step required to dynamically resolve the symbols in the executable. There is a runtime cost for the flexibility that shared libraries offer. However, most users are aware that a program can take a few seconds to load. In most cases, this cost is not a huge problem. If you're interested in more details, any decent book on operating system design will have a section related to dynamic linkers and how they are implemented.
There are several keywords in C++ which can affect how a program is linked. Adding the keyword inline to a function instructs the compiler to drop the code in anywhere the function is called. This is only a suggestion to the compiler, and it can be ignored. The original idea of an inline function was to inform the compiler that the current function is small and simplistic. The time to execute the function is less than the overhead required to make a function call. Modern compilers essentially ignore the inline keyword when making optimization decisions because their knowledge of the target platform and the function call overhead is more finely tuned. However, when you add the inline keyword, there is a fundamental requirement the compiler must observe, regardless of its optimization decisions. The compiler must mark the symbol for this function as weak, which will have an effect during linking. This means on modern compilers, the inline keyword has very little to do with optimization. Another way to affect linking is to force a symbol to have internal linkage by placing the code in an anonymous namespace. Prior to C++ 11, the standard did not specify the linkage for symbols declared in an anonymous namespace. This example shows code in an anonymous namespace. By definition, both the variable isNice and the class gingerbread will have internal linkage. This means symbols in this namespace can only be accessed from within the current translation unit. It is worth noting that anonymous namespaces in different translation units are not merged. If this example code was located in a header file, then every translation unit where it appears will have its own copy of the variables and the class. If you attempt to pass an object of type gingerbread to another translation unit, which is using a different copy of this class, you will receive a link error saying there is an undefined reference. Just to be clear, it is not a good practice to put an anonymous namespace in a header file.
There are two main types of errors that can occur during the linking process. The first is when two different object files have a strong symbol with the same name. The linker will report a duplicate symbol error when this occurs. The most common reason this happens is when a function is implemented in a header file, but not marked inline. Each translation unit has its own copy of the function, but since it was not inline, all of the generated symbols for that function are strong. The other common error is an undefined external. This usually means that one of your translation units refers to some entity, but that entity was never implemented. For example, if you have a function declared in a header file, but not implemented in any translation unit, the compiler will not report any errors. However, at link time, none of the calls to that function can be resolved because the implementation is missing. When resolving link errors, it is a good practice to test your design and assumptions on multiple platforms. If you have developed a library and only tested on Unix, you may not discover some of the undefined externals until a user reports a problem. It is worth noting that testing your application should involve starting the program and using every feature that may depend on a shared library. For more information about the CopperSpice project, please visit our website at www.copperspice.com.
Thanks for watching. We hope you found the content of value. If you have any questions or feedback, feel free to leave a comment on this video or send us an email.
Please make sure you subscribe to our YouTube channel and come back in a few weeks for our next video.